Welcome to the Unit 8 Section 1 video on identifying quadratics. The function y equals x squared is shown here in the graph. Notice that the graph is not linear. This function is a quadratic function. The shape of a graph is called a parabola and looks like a U. There are three different types of quadratic equations. You have standard form, which is in the form of y equals ax squared plus bx plus c. Vertex form, which is in the form of y equals a times the quantity x minus h squared plus k. And you have intercept form, which is y equals a times the quantity x minus p times the quantity x minus q. Quadratics will always have an exponent of 2, either explicitly stated as in standard or vertex form, or as a result of multiplying two x terms together, which you see in intercept form. So let's determine if each of these functions is a quadratic. So for a, we have an x squared term. There are no powers that are higher than the x squared term, so this is a quadratic. For b, there's an x squared term, but there's also an x to the third term. So if you have a power that's higher than 2, it's not quadratic. For c, there is no x squared term. We have 3x minus 1. This is actually linear, so it's not quadratic. For d, we have the quantity x minus 1 squared. So if we were to multiply this out, we would end up with an x squared term, so this is quadratic. E has an x squared term, so that is quadratic. F has an x squared term, but it also has a y squared term, and you cannot have a y squared term, so that's not quadratic. For G, we have an x squared term, but you also notice that we are cubing a binomial, which means we're going to end up with an x cubed term somewhere, so this is not quadratic. H has no exponents on any of the variables, so this is linear, so it's not quadratic. I is quadratic because we have an x squared term. So that one should state that it is quadratic. For J, we have 4x squared, and we have a 2x and a 4x, which would just be like terms, so this one is quadratic. For K, we have x plus 2 quantity squared, but then we would multiply that x squared by the x in the x minus 4 term, so this one's not quadratic. And then finally for L, when we multiply out 2x and x, we get an x squared, so it is quadratic. The graph of a quadratic function is a curve called a parabola. Parabolas can be oriented upward as shown previously, or downward as shown here on this slide. Keep in mind that parabolas turned on their sides are not quadratic functions since they fail the vertical line test. The graph of a quadratic is the set of all solutions to a quadratic equation plotted in the coordinate plane. To graph a quadratic function, generate enough ordered pairs to see the shape of the parabola. Then connect the points with a smooth curve. So in A, we have a parabola, but it's on its side, and it fails the vertical line test, so that one's not quadratic. For B, we have a parabola, so it is quadratic. C is not a parabola, it's two straight lines, so it's not quadratic. D is just a line, so it's linear, it's not quadratic. E is a parabola, so it is quadratic. F is also a parabola, so it is also a quadratic. G is not a parabola, so it's not quadratic. H is a parabola, so it's quadratic. And I, well, first of all, fails the vertical line test, but it's just a circle, so it is not quadratic. Previously, you identified linear functions by finding that a constant change in x corresponded to a constant change in y. The differences between y values for a constant change in x values are also called first differences. So, taking a look at a quadratic relationship, you have constant first differences, meaning that the x value changes by the same amount each step of the way. But if we look at the first differences, we do not have a constant change. We add 1 the first time, then we add 3, then we add 5, then we add 7. But it's not the first differences that we're interested in. We are more interested in the second differences. So from 1 to 3, we add 2. From 3 to 5, we add 2. From 5 to 7, we add 2. So since our second differences are constant, then we can say that we have a quadratic function. Notice that the quadratic function does not have constant first differences. Instead, it has constant second differences. This is true for all quadratic functions. So in this example, let's determine if each table of values represents a quadratic function. So first, we're going to check the first differences. And in this case, the differences in our x values are all 2. We add 2 each time. In our first differences in our y's, we have minus 6, because 8 minus 6 is 2. Then 2 minus 2 gives us 0. 0 plus 2 gives us 2. And 2 plus 6 gives us 8. So our first differences are not constant. But of course, we're not expecting them to be constant when we're looking for a quadratic function. Instead, we have to check our second differences. So to get from negative 6 to negative 2, we add 4. To get from negative 2 to positive 2, we add 4. To get from positive 2 to positive 6, we add 4. So since we have a constant second difference, we do have a quadratic. For b, again, our x values have a constant change. So now let's check our first differences in our y's. We have minus 8, minus 4, plus 6, plus 22. Now let's check our second differences. We add 4, then we add 10, and right there, we can already say that it is not quadratic because we do not have a constant second difference. Just to complete it, you can see further on, you add 16, it's most certainly not a constant second difference, so therefore it is not quadratic. A set of ordered pairs is a set of x values with their corresponding y values. To determine if a set of ordered pairs is quadratic, write the ordered pairs in table format and determine if the second differences is constant. So here's a couple of examples of some ordered pairs. We're going to put it in table format, and then we're going to do what we just did with the table. We'll check our x values, then we'll check our first differences, and then finally our second differences. And here in A, we found that we do not have a constant second difference, so therefore we do not have a quadratic. If we take our values in B and put them in a table, we check our x differences, and those are the same. Our first differences in our y, then our second differences in our y are constant, so therefore we have a quadratic. When presented with a real-world scenario, it is helpful to visualize what is being modeled. For example, a soccer player kicking a ball would be quadratic since the shape of its flight path is a parabola. Remember, another way to write the output y is by using f of x. So the height of a soccer ball would be a function of time, or h of x, where h is the height and is a function of time, t. So you may see it represented as h of t in a case like that. So we're going to determine if each real-world scenario would be modeled by a quadratic function. So let's take a look at the area of a square is a function of the length of the side of the square. So let's draw a picture. Here's our square, and if we say that each side is x, to find the area of that square, we multiply the length times the width, which in this case, both are x, so it's x times x, which is x squared. Now we can write a function f of x equals x squared, and that most certainly is quadratic. So this situation is a quadratic function. The height of a diver is a function of time. So we have our picture here. We have a diver, and over time, the height of the diver increases to a maximum point, then falls until reaching the surface of the water, forming the shape of a parabola. So this would be a quadratic function. The amount Jeremy tips at a restaurant is a function of the total bill. He tips 15% of the total bill. So the input here is the amount of the total bill. The output would be the amount tipped. So the function would be 0.15 times x, which is your total bill amount, and that would give you what his tipping amount would be. Well, that is a linear function. There is no x squared term, so therefore this is not a quadratic function. Fernando hits a baseball upward from an initial height of 3 feet. The baseball hits the ground after 2 seconds. So think about the flight path of a baseball. Over time, the height of the baseball increases to a maximum point, then falls until reaching the ground, forming the shape of a parabola. So that gives us a quadratic function. Rachel works at a hair salon. She makes a flat rate of $30 per day, and then she makes $15 per customer that she sees each day. So the input is the number of customers, the output is the amount made per day, and the function that would model this is the $30 that she makes in the day from the flat rate plus the $15 per customer. This is a linear function. There's no x squared term, so this is not a quadratic function. And then finally, the distance a ball travels after being dropped is a function of acceleration and time. The distance is 1/2 of the acceleration multiplied by the square of the time. So if we simply take that sentence and write it out and interpret it as an equation or a function, we get d of t is equal to 1/2 a, where a is the acceleration, times t squared, where t is time. So there is a t squared term, which means that this is a quadratic function. Thanks for checking out my video in the Foundations in Algebra series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.